One student joined. Kalyan Kumar, can you hear me?
Yes, sir.
Will
Yes,
others
sir. Yes, sir.
will others join the class?
I don't know. తెలియట్లేదు సార్ వాళ్ళు ఎవరు రిప్లై ఇవ్వట్లే.
మీకేం చెప్పలేదా ఎవరు వస్తున్నారు ఎవరు రావట్లేదని?
చెప్పలే.
మీకు ఎవరు చెప్పలేదు జాయిన్ అవ్వద్దని?
చెప్పలేదు సార్ ఇంకా.
ఓకే, సో జస్ట్
గ్రూప్ లో మెసేజ్ చేస్తారు.
యా. Kalyan,
సార్
if nobody is coming, would you like to listen to the class?
నో సార్. ఎవరు రావట్లేదు, ఎవరు రిప్లై ఇవ్వట్లేదు సార్ మెసేజ్ చేశా కానీ.
Acha. So what we will do?
5 minutes చూద్దాం.
Okay, we'll wait for 5 minutes and see.
5 minutes.
Guys, is my voice audible? Is my voice audible, guys?
Yes, sir.
Yes, sir, you are audible.
Okay, so I will share my screen. Will be able to listen to this class? Were the slides visible?
Yes, sir.
Yes,
It's
sir.
visible.
Okay, so it's already 20 minutes. We will try to see today binary search tree and AVL tree. I'll just go through briefly. Later I'll upload the slides so you can go through it again. If you have doubts, you can feel free to ask. Okay. Uh, in the previous class, we discussed binary tree. We discussed that how we can build a tree, how to insert an element, how to delete an element, how to traverse a tree using in order, pre-order, and post order. Okay, so there are various types of binary trees. Each binary tree has its own properties. For example, today we will see binary search tree and height balance tree, which are in blue color. But later you will encounter Huffman tree, which will help you in compressing your data. You will study in the future. Maybe you would have studied, I don't know. Huffman tree will help you to compress the data. And also heap is also one of the beautiful data structure. But due to lack of time, we will not discuss heap tree and Huffman tree. But if time permits, after covering your syllabus, if time permits, I'll discuss. But in your syllabus, there is an mention of B tree. B tree also we need to discuss if you refer the slides. In order to understand B tree, you need to have some idea about binary search tree and height balance tree. So that is also known as AVL tree. We will try to discuss these two things in today's class. After that, after midsum break, I'll discuss B tree and graphs. These two things we'll discuss, then we'll go to operating systems. So let us see what is a binary search tree is. We studied, given a number of elements in an array, the worst case possibility to find an element in a given list will be order of n. Worst case, the element will be maybe at the last position. Then you need to compare each and every element whether the element is there or not, or if the element is not there, in order to make sure that you have to scan the whole array. So if you have n elements in your array, then you complexity will be order of n. That would be the case even in binary tree also, but binary search tree, as it's the name itself says, that it is a simple mechanism of a tree representation. We will put some conditions, some restrictions in the data when we are building the tree that will help us the complexity of log n. It will reduce the complexity worst case to log n. That how it will happen, I will show you. Okay, so in a binary search tree, all the elements, when you are constructing a tree, all the elements that are less than the root will be placed towards the left side. All the elements which are greater than the root will be placed on the right side. So the left subtree node contains only the nodes which are less than the nodes of the root. The right subtree are less than the parent. Likewise, the when you are building the right subtree, the nodes which are greater than the parent will be placed. Okay, so likewise you are building a tree. For example, see, this is the root. The left side, the data should be less than the root. The right side data should be the greater than the root. For example, your 7 is the root. You see this, all the elements, 4 is less than 7, but 9 is greater than 7. You take 4, 2 is less than 4, but 5 is greater than 4. But elements which are on the left side should all of them should be less than the root. For example, although 5 is greater than 4, but 5 is less than 7. Okay, so you are building a tree in a such a way that all the elements less than the root will follow the left side, all the elements greater than the root will follow the right side. So for example, this guy, so 3 is less than 1 is less than 3, that is correct. 3 is greater than so 6 is greater than 3, this is also correct. 6 is greater than 7, this is also correct. But 6 is less than 2, if this is the subtree, that is correct, but it is not violating, it is not keeping the property of the root with respect to root. So this is not a binary search tree. Okay, does this make sense? A simple binary search tree is you keep the elements which are less than the root on towards the left. When you're building itself, we need to keep one node at a time. Okay, so this 2 nodes should come to the left side. Maybe it can come left side to the 1, then 1 towards the right side, because 2 is greater than 1. This node should come towards the left subtree of right node of parent 1. Okay, so if you're building all the elements which are less than that towards the left side, greater than the elements towards the right side, we call that as a binary search tree. There are many operations when you build the tree. What happens? Suppose I want to find an element 5. 5 is there or not? What I'll do, I'll compare with the root. When I compare with the root, I'll see that 5 is less than 7. So I will not search the right hand side. I will go only to the left hand side, because I know that this element will lies towards the left side. Okay, so the element will go to the left side. Here again with this node, it will compare 5 is greater than 4 or less than 4. If the element itself, the 3 conditions it will check. So 5 is greater than 4. So all the left side it will not search, only the right side it will search. So you see that you have 1, 2, 3, 4, 5 elements. Worst case, if you want to find the 5, you need 5 searches. But now how many searches you need? Only 1, 2 searches. Within 2 searches you found the element because of the property of binary search. So you can find what is the minimum element. The minimum element will be, you can easily find the whatever the left leaf node, leftmost leaf node is your smallest element, rightmost right node will be your maximum element. You keep traversing towards the left and left and left and left till you reach the null node. That will be your smallest node. You keep traversing towards the right node of the right child to the right node till you encounter the null. Then that node will be your maximum node, right? So finding a maximum or a minimum element in a tree will be very easy. Inserting an element, deleting element is a bit tricky, but we can have this other auxiliary operations. So since the root is always between the left subtree data and the right subtree, performing in-order traversal of a binary tree will always produce a sorted list. Do the in-order for this tree. What is the in-order traversal for this tree? Can anyone tell? What is the in-order traversal? In-order is left subtree, root, right subtree, correct? In order is left subtree, root, right subtree. So you go to the left subtree, you will encounter 2. 2 will be printed first, then root, 4 will be printed second, then right subtree, that is 5. You encounter null, then you go to again root, 7, then you print 9. This is your in-order traversal. You see this? The in-order traversal of a binary search tree will be always in a sorted order. Okay, 2, 4, 5, 7, 9. It will be in a sorted order. So it produces sorted order. So this is what I have been explaining here. Performing traversal produces sorted list. So solving problems, first we process to the left subtree, then root, then finally the right subtree. Depending on the problem, okay, we will try to see uh, how to do that. Okay, now when we are searching an element, if the left subtree is less than the element we want to search, then we will skip it. As I told, if you are searching for an element, if the left subtree root data is less than the element, then we will not search the left side, we will only search the right side. The same case with the, if the element is greater, the element you want to find, the element you want to find in a tree is less than, suppose 9 you want to find, you will compare 9 with 7. If 9 is less than the root, okay, I mean the root element is less than the search element, you will not search the left side, you will search only the right side. If the root element is greater than the search element, then we will search only on the left side. Does this make sense what I'm saying?
Yes, sir.
Okay, so suppose you want to search 6, you will compare 6 and 7. So 7 is greater, so you will not search the right side, you will only search the left side. Likewise, okay, so that's what we have written here. The same with the right subtree. So binary search tree takes less time because it will take only height of the tree. Okay, whatever the height of the tree, worst case that height only will take, the height of the tree will be always log n. Okay, so that's where we are, the worst case complexity we are decreasing to log n. But even in binary search tree there are exceptions. Only a skew tree will take order of n worst case time. What is a skew tree? I will tell you. uh, okay, so this is the algorithm. So if the root is null, there is no elements to search. If root data is less than the root data, then go to the left direction. If data is the greater than the root data, then go to the right direction. You keep doing this recursively, you will be able to get the element. This is finding an element in the binary search tree. So this is also the same. If you don't want to call recursive function, you can use the other way. If data is not equal to root dot data, then return root. Else if you go to the right, else you go to the left. Okay, you keep calling till your element will become null. This is non-recursive element. Okay, so the complexity is this much. So you can see here finding an element. Suppose you want to find 4, you compare these elements. 4 is greater than 10 or less than 10. So we will not search this. We will come to the left direction. We'll keep coming to the left direction. Again, we'll compare 4 and 6. So 4 is less than 6. So again, you come left. Within 2 searches, you found that element. Right? So in worst case, this could be order of n. That's how the binary search element will work. This finding the minimum element will be always the leftmost leaf node will be your minimum element. The maximum element will be the rightmost child of in a tree of in the BST will be your maximum element. You can say that 16 is a maximum element. Okay. So this is the simple code how you can find the minimum element in a binary search, and how to find a maximum element. So this you can see here that the node left subtree of this node will be always less than the root. So the node which has the maximum will be the rightmost subtree, which is 16 in this case. Okay, so this is the code. You can see this. Okay, so likewise, we can insert in data where you can insert in data. Suppose you want to insert 5, you will compare here. 5 is less than 6, you should come left side. Then 5 is greater than 2, you should go again right side. 5 is greater than 4, you should go to the again right subtree. You should insert at a proper place. When you're inserting an element, you keep comparing so that the binary search tree properties will be preserved. So you can keep inserting at the proper place. So this is the code for that. You go through it. Likewise, for deleting a node, you need to consider 3 cases: how to delete a leaf node, how to delete an exact one child, how to delete 2 childs. If it is a leaf node, you simply delete it. There is no problem. Make it 2 right child as a null. Okay, the parent right child as a null. So there is no problem. If you want to delete an element which has the other way, then you need to understand what is in order predecessor and successor. So if x has 2 children, then in order predecessor is the maximum value to its left subtree, and its in order successor is the minimum value in the right subtree. So this is the x. The maximum value in the left subtree will be lies here. Minimum value in the right subtree will be lying here. This is the successor. This is the predecessor. Okay. So why we are happening when we are deleting an element? Suppose you want to delete the root 50. In order to delete that, we need to keep reconstruct the binary tree in a proper way. Okay. So in order successor, right subtree left node 52 you will keep with the root node. Then you will exchange these 2 nodes. If you want to delete this node, leftmost right subtree's minimum value will replace. 50 will be replaced by 52. Then the remaining values will keep the same. You delete this node. Okay, so this is how the binary search tree works. But what happens? This is a perfect balanced binary tree. And when you calculate the height is the height of this node. The height of this node minus this node will always be great. I mean, it will be 0 or 1. Okay, the height of this node 4 is 2. The height of node 2 is 1. 2 minus 1 is 1. Likewise, okay. When you calculate the height of a tree, this is a perfectly height balanced tree. Okay, you can see that 0 and 1, 0 and 1. This is a perfect full balanced binary tree. but this is it's a balanced tree. The height between every node is 0 and 1. You can have unbalanced tree. This is a height unbalanced tree. When you calculate the height of this node is 2. Okay, because the height here is 1, 2, 3, but here is 1. 3 minus 1 is 2. Okay, so this is unbalanced tree. In order to make a tree balance, we will do some operations. We will do some rotations. These are the rotations how we are doing it. Suppose this is your X node. If you want to change, you will simply do the left rotation. Then your node W will become root, X will go down, B and C will be your B right child will map to X left child. When you make such rotations, your tree will become again balanced. Okay, these are the 4 possible rotations. Left rotation. Then, for example, this is the example 6, 5, 3, 9, 8, 7. You want to make it a balance. You make simply 8 as a root. 9 will become the right child. 7 will become the left child. It's a simple left rotation, single rotation. Now this tree is balanced. Okay. So likewise, right rotation, the balance is coming on the right hand side. So you have to do the reverse process of the previous case. Suppose this is one example. There is some unbalance here. So what you'll make is, instead of uh, here 19 will make root, 15 will make left child, 29 will make right child. You are making it balanced. The height will be balanced. Okay. Likewise, there are 2 more operations are there. So you go through them and go through these slides and let me know if you have any doubts. Because many students are not there, we will not discuss too much. I'll upload this slide, go through the slides, and if you have any doubts, we'll discuss in the next class. Is that okay?
Okay, sir.
So these are the few things we need to remember when we discuss about B trees. Just go through binary search tree and AVL tree. Okay, let me upload the slide, then I will stop the class. Okay, uploaded the slide. You can check whether you'll be able to see the slide or not. Lecture 15, binary search tree and AVL tree. Can you able to find?
Yes, sir. It's visible. Uploaded.
Yeah, please go through the slides. If you have any doubts, let me know. Okay. You want to ask any question?
No, sir.
Okay. If you don't have any questions, we will stop now. You go through the slides as I told. If you have any questions, you ask me in the next class. So we will stop now. We will continue after the midsummer break. Okay.
Okay, sir.
Okay.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.